Welcome to the first module of 4.6, Related Rates. This module is going to focus on Pythagorean Theorem, right triangle problems. And pretty much what connects every question you'll see in this module is that there will be a right triangle that we're dealing with. So related rate problems, we'll talk about a lot of different topics, but if it ever talks about a ladder sliding down a wall and they tell you how long the ladder is, usually they'll want to know either how far away the ladder is from the building or how far up it goes. There's a clear-cut right triangle in that picture. If you also imagine two moving objects, one going north, for example, and another going west, as they move apart from each other, a right triangle is being formed in that diagram. Finally, if you get a question that just says, hey, there's a right triangle and the side lengths are changing, again, that's a clear-cut, obvious choice of knowing that it's going to be a Pythagorean theorem situation. So, in order to get to the actual problems themselves, we first need to cover the essential skills. So, you need to know what the Pythagorean theorem is, which is a squared plus b squared equals c squared. Sure, you guys have seen that before, but you must know how you use it. So in order to get to that, let's look at a couple examples and examine how they are different. So, starting with this first example of a right triangle, we know we're going to use Pythagorean theorem for this because whenever you have two given lengths of a right triangle and you're missing one, the formula a squared plus b squared equals c squared is the key. Now, the only thing I make a big deal of with Pythagorean theorem is this. The hypotenuse, the longest side, the side across from the right angle, the slanted side in most situations, must be your c, be in place of your c. Other than that, I really don't care what order you put the a and the b. So in this case, I'll go with 36, which is 6 squared, plus 64, which is 8 squared, equals s squared. Now, in this case here, most people just know you have to add the 36 and 64, meaning in order to solve for s, we would simply take the square root of 100, which brings up a very important Pythagorean triple in this case. Hope you guys are aware that this is simply a multiple of the classic 3, 4, 5 right triangle. Double all those values, you actually get 6, 8, and 10. So in this case here, the answer for this problem is simply 10 miles for that missing side. Okay? Pythagorean theorem can always be used in this exact same way, but there is a difference when you deal with questions like this one. If you notice the difference right away, even though we are going to use Pythagorean theorem for it, being a squared plus b squared equals c squared, my question is this: what is the hypotenuse? Well, this time it is not the missing value. So when you take 13 squared, you get 169, and the important thing to notice now is x has to show up as either your a or your b. And again, it doesn't matter which one's which, so let me just go ahead and plug that in for a, making b squared 25. So when you compare the difference between these two questions, we don't add in this case. Hopefully everybody has seen questions like this before, where you actually need to subtract the smaller perfect square from the other one. This will give you 144, which again brings us to another very, very common Pythagorean triple. You take the square root, you will get 12 as your answer for this, meaning that for this triangle here, we would get 12 miles for the missing side. 5, 12, 13 is another very common Pythagorean triple that we'll be seeing a lot. So, the Pythagorean theorem is a pretty easy theorem to use as long as you keep track of which side you're solving for and making sure that you go through the steps properly. Okay? Now, the other essential skill, other than just using Pythagorean theorem, is knowing how to take the derivative of Pythagorean theorem. Now, we've studied derivatives before, and you've also learned about implicit differentiation. This is a very convenient situation whenever you need to take the derivative of a formula that has multiple variables, and if you notice, the key being this. When you're taking this derivative, notice it is with respect to time. In related rate questions, everything is going to be based on time. So in these situations, you'll notice that we don't have a t anywhere for our variables, yet we want to take the derivative with respect to t. So what does that look like? Well, you might recall this from earlier. However, the derivative of x squared is 2x. However, with implicit differentiation, you have to remember to multiply that by the derivative of x with respect to t. In other words, dx dt. Now, if I said take the derivative of y squared, hopefully you guys recognize that it would just again be 2y, but again, times dy dt. And finally, the derivative of s squared, we can of course say 2s times ds dt. And that's our derivative of the Pythagorean theorem. Now, if you notice here, we have a very lengthy equation now. Whatever you can do to simplify it is recommended. So in this case here, let's go ahead and cancel out the 2's, since we could divide both sides of the equation by 2. So this leaves us with something that you'll be using quite a lot during this module. The derivative of Pythagorean theorem, the formula we'll be using, actually has 6 different variables. It has x. It has the variable dx dt. It has y and the variable dy dt. Finally, it has the variable s and the variable ds dt. Now, one thing I want to mention now is this. When using Pythagorean theorem, x, y, and s, those represent the lengths of the sides of the triangle. In other words, let me get some room here. X, y, and s represent side lengths. Much like the question we just solved earlier, where you have to use Pythagorean theorem to solve, those 3 letters, those variables in this equation, represent how big the sides actually are. Now, why am I making a big deal of this? Well, it's because of the other variables. This one, and this one. Those are variables as well. Now, you might recognize those as looking like derivatives. Well, it's important to realize this. dx dt, dy dt, and ds dt. Those are derivative variables, meaning those represent the rate at which the sides are changing. Now, since derivatives measure slope and the way that things change, in word problems you can interpret that as anytime you have a rate, like 50 miles per hour, that represents a derivative variable. So if you ever saw 50 miles per hour, it would never get used for x, y, or s. It would get used for either dx dt, dy dt, or ds dt. Now this will be very, very important when we get to our first problem. So remember our formula right here, x dx dt plus y dy dt equals s ds dt. And those are 6 different variables, and we're going to need to plug in a lot of values into those. The first example we're going to look at is example A, 90-degree intersections. Now, when you read this problem, you'll actually find out that there are 2 moving vehicles. One of them is a police cruiser moving south toward an intersection, and is chasing a speeding car that's moving to the east that has already turned the corner. Now, with 2 objects in motion in these directions, there's going to be a right triangle that gets formed as you try to measure the distance between these 2 vehicles. When you read this problem, there's a lot of information, a lot of numbers being thrown your way, a lot of miles per hour. So the key is this. Once you read the question to yourself and kind of figure out what's going on, it's important to start getting a grip on what are the things that are moving and changing in this problem. So here's what I do. I'm going to go through the actual question and just start reading the different parts that I feel like are important in this story. So first of all, they tell you that you have a police cruiser and that it's approaching the intersection from the north. Now it's chasing a speeding car that has turned the corner and is already moving toward the east. So when the police cruiser, they tell you, is 0.6 miles, so they're telling you about the first car that is traveling from the north. When it's 0.6 miles north of the intersection and the other car, the speeding car, is 0.8 miles to the east, they say that the police determined using radar that the distance between them and the car, the distance between them and the car is increasing at a rate of 20 miles per hour. Now, they ask, or finally get to our question. It says if the police cruiser is moving at 60 miles per hour, at a rate of 60 miles per hour, at the instant of measurement, then what is the speed of the car. Now, looking at this paragraph, all I've done is highlight these different pieces of information, but I hope you guys can distinguish that there are three things we're measuring. The police cruiser and how fast it's moving, the speeding car and how fast it's moving, and finally the distance between the police cruiser and the speeding car. We need a diagram to put all this into perspective. So, what I'll do here is show you guys what diagram I would set up in order to get this problem looking more like a math problem. So first, the intersection. Let me put together a couple things. Now for our intersection, if you notice I'm not drawing the entire thing. If I know one car is coming in from the north and the other is going east, those are the only parts that I need to make sure I get correct. Now they do tell you it's a right-angled intersection so that we can create our right triangle. So let's get the police cruiser drawn on here. Police cruiser is coming in from the north. I know, it's a beautiful picture. And the speeding car is zooming out toward the east to try to get away. Now if you want to spruce up your picture, go ahead. If you want to give little lines of motion symbolizing that that car is technically traveling south and the speeding car is zooming off in this direction, going that way, go right ahead. Now the idea that is really important to catch is this. They tell you that the distance between the police cruiser and car is something that is being measured in this case. So the distance between them, I will draw like that, which now I hope everybody can tell we are looking at a right triangle diagram, which is why Pythagorean Theorem is so helpful here. Now in this diagram, let's use variables to keep track of what all these different things are. So for the police cruiser, if you look at what's changing, the distance between the police cruiser and the intersection is a certain amount. And if you notice as the car travels south, that's something that will be changing. So let's give it a variable. I want to call that variable y to represent, I don't know, a vertical distance in this case. So guess what we'll call the distance between the speeding car and the intersection? You guessed it, that will be our x. That's how much that distance, or that's what that distance will be represented by. Now, look carefully at this diagram. If you think about it, y is going to be a value that's shrinking, and x will be a value that's growing as the situation unfolds. But there is one more variable we need. The distance between the two vehicles right here is something that will be changing as the other two cars are moving. So we need another variable for that. You can call it d for distance. I like to use s for the slanted side. Okay? Now, this is where the fun begins. We have a right triangle diagram with our variables labeled, and the most tempting thing right now is to try to plug in numbers. Please do not. The key idea is this. If x, y, and s are constantly changing, what we need to do is come up with an equation that uses those three variables that relates them all together, hence related rates. So what equation could we use with these three variables, x, y, and s? How are they all connected? Well, this is the point of what we started with, you guys. The formula we will use will be x squared plus y squared equals s squared, the Pythagorean theorem. The great thing about this module, folks, is that every single problem will use this equation in some variety. Now, before we get to actually plugging in numbers, the idea is we want to take the derivative of this entire equation with respect to time, like we said before. So remember that this derivative will actually involve implicit differentiation. And if you've forgotten what that's going to look like, let me just show you real quick here what we're going to have. We'll go with 2x, but then times dx dt, since we're taking this derivative with respect to time. Then plus 2y dy dt, and that's going to be equal to 2s ds dt. The calculus in this problem is actually very simple. That's the only thing that you have to keep track of for our derivative there. Now again, make your life easier. Let's cancel out 2's on both sides, giving us this equation to work with. X dx dt plus y dy dt is equal to s ds dt. Okay? Now, like I said before, we're looking at an equation right now with 6 variables in them. If you want to solve for a missing variable, you need to plug in numbers for all the rest. So what I'd like you to do is this. Our goal in this, from here on out, is to figure out what's going to go in each one of these blanks. 6 variables. We need to have something in all 6 of these sets of parentheses. Now, remember all that stuff we were highlighting before? Let's take a look now and see if we can shed some light in terms of what these things can represent. Okay? Starting from the very beginning, let's see if we can assign each value into a variable. So a police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner, now moving east. When the police cruiser is 0.6 miles north, what variable is that? Well, this variable represents how far the police car is from the intersection. If your units are miles, then it's not going to be a rate, you guys. This is going to be our value for y. That'll be 0.6 miles. Now they tell you that the car is 0.8 miles to the east. What variable is that? Well, again, a distance here is going to be represented by the variable x. So we will say that x equals 0.8 miles. Now here's the interesting one. As we keep going, it says the police determined with radar that the distance between them here, they don't tell you what it is, but they say is increasing at a rate of 20 miles per hour. When you see those units miles per hour, you know this is going to be a rate situation. So let me write down for this. Instead of s equals 20, that would be incorrect. We want to say ds dt equals 20 miles per hour in this case. Now, this is the one that is probably the most tricky of everything. They ask if the police cruiser is moving at 60 miles per hour. I know what you're probably thinking. If it's miles per hour and it's the police cruiser, that's this amount. So instead of saying y, you probably have guessed that it's going to be dy dt. But what is it equal to? 60? Not quite. Remember when I told you that this distance here, represented by y, is how far away the police car is from the intersection. If the police car is traveling at 60 miles per hour, is this distance getting smaller or getting bigger? It's getting smaller. So for every rate you ever see, you must remember this key fact. It's either positive when the distance is increasing, or it's negative if the amount is decreasing. So instead of saying 60 miles per hour, we must say negative 60. Now, to finish things off here, guys, the final part about this question actually tells us that they're asking for the speed of the car. The speed of the car. In other words, they want to know how fast is this distance right here, x, changing. So in other words, they want us to solve for dx dt. That's the part of the question we need to solve. So this is actually pretty fun. Once you have all this information straightened out, let's put all the information where it should go. So 0.6, that's supposed to be for y. Let's put that in there now. 0.6 goes right there for y. The dy dt variable is negative 60, so let's put that right here, a negative 60. Okay, we can multiply that later. Next, we've got our x value is 0.8, so let's go ahead and put our 0.8 where it belongs, right here. And if you look at it, we need to solve for dx dt. So if that's the case, let's not fill anything in for that, or not fill in a number, but let's just write the variable dx dt. And now we know that we are actually going to solve for this missing amount. So there's only 2 more things to fill in, right? Let's get our ds dt, the 20, into our ds dt. And put the 20 right here. And wait a second. There's something missing. There's no value for s. If we don't have a number for that, we're not going to be able to solve for our missing variable. So here's the key to this question and almost every related rate problem you'll ever notice. Once you've drawn your diagram, taken your formula, taken the derivative, done all your cancellation, and started plugging in all your values, there's usually going to be something missing. And the idea to understand is this. What is s? It's the distance between the two cars. What if I told you that even though everything in this problem is moving, there is a moment that this problem talks about? And let me draw a diagram to show you this. Okay? Sometimes it's helpful to have a second picture. In our right triangle, they do tell you, at the moment that we're wondering about, they tell us that the distance that the police cruiser is from the intersection is 0.6. They tell you that the distance that the speeding car is 0.8. In that exact moment, my challenge to you is, can you solve for s? I'd like you to pause this video now, and I want you to solve for that missing value of s using what we did earlier, the Pythagorean Theorem. Good luck. And welcome back. Hopefully you paused to solve this problem here, but if you use Pythagorean Theorem correctly, here's what you should have gotten. A squared plus b squared equals c squared. You should have gotten 0.36 plus 0.64 equals s squared. Ironically, does this look familiar? This is a variant of our Pythagorean triple from earlier. If you do this correctly, you should get 1 equals s squared, which means s is equal to 1 in this problem. If you notice, this is very similar to 6, 8, 10, only divided by 10, 0.6, 0.8, and 1.0. So the key for that is to realize that even though the problem doesn't tell you that valuable piece of information, you can find it by using what the problem's already about. So I'm going to go ahead and plug in 1 here now. And if you look at what we have, we've got an equation that we can easily solve as long as you're willing to calculate a few things. So we have 0.8 dx dt minus 0.6 times 60, which will give us 36, equals 1 times 20, which is 20. Solve for dx dt, please. So let's add 36 to both sides. That'll give you 56, and then divide both sides by 0.8, and you will get dx dt, that's a t, equals 70. Now, what is dx dt again? It's the rate at which x is changing, so this must be miles per hour. And ladies and gentlemen, there is our final answer. Going back to our picture, the question asked us what is the speed of our car. Now I hope everybody can tell, while the police car is traveling downward at a rate of 60 miles per hour, and the distance between them is changing at a rate of 20 miles per hour, using the information in the problem, we can now figure out the speeding car must be going 70 miles per hour. Now our second example, example B, is about a falling ladder. Anytime you're dealing with a ladder leaning up against a building, what the question's really wanting you to analyze is how is the triangle that's formed changing? So, as you read through this question, there's a few key things to realize. The ladder itself, they tell you is 13 feet. You guys, that's not going to change. A ladder does not magically grow or shrink at your command. It's going to be 13 feet this entire time. We call that constant. Now they tell you it's leaning against a 20-foot vertical wall. That wall will also not change height in this case. A wall is a wall, and they tell you it's 20 feet. Again, constant. But the ladder begins to slide down. So what starts to change? Well, it says during the process, the bottom of the ladder will be sliding away from the bottom of the wall, whereas the top of the ladder will slide down the vertical wall. So what you want to try to imagine, again, you guys, is once you read the problem and understand what's happening, you want to go through the question and try to figure out what pieces go together. So let's start with the following information. The ladder, they tell you, is 13 feet. Okay? They also tell you that the wall we're dealing with is 20 feet. Now, when the ladder begins to slide, here's the two pieces of information you'll really want to keep track of. The bottom of the ladder is sliding away from the bottom of a wall, and here are the magic words, at a rate of 0.5 feet per second. From the previous problem, you know that miles per hour meant a rate. For this question, feet per second give you the clue that it's going to be a rate. Also, they say the word rate, so there you go. Now, at that time, it also says determine, or this is the question, determine the rate at which the top of the ladder, so the rate at which the top of the ladder is sliding down the vertical wall, when the tip of the ladder is exactly 5 feet above the ground. Now again, there are some elements to this that really demand a picture that help us understand this, understand the situation. So let's get a picture drawn for our problem here. So we have a 13-foot ladder leaning against a 20-foot vertical wall. Well, here's the ground. Here's the 20-foot vertical wall, and let me just go ahead and say 20 for that now. Okay, and the ladder is 13 feet. Now, 30 is not going to reach all the way up to 20, so let me just draw the ladder like this. And if you want this to look like a ladder, go ahead. I know, beautiful art. It's also magically not touching the building. Okay, there we go. So there's our ladder, and that's 13 feet. And again, we can write that number in because that is not going to change during this question. Now, be very careful with this. If you look at what is going to change, it's the distance between the bottom of the ladder and the bottom of the building. So that distance there requires a variable. So let's go ahead and give that a variable here. And what shall we call that? How about x? Then for this next question, what should we call that distance? Let's call it y, the distance from the top of the ladder to the bottom of the building. Now, here's the weird part about this question. How does 20 factor into this? If all we care about is how high the ladder reaches, these are those weird situations that do come up where the number 20 isn't even really needed. Sometimes you will get problems, you guys, where there's too much information. And sometimes you don't need to plug in every number into a problem in order to solve something. This is one of those situations where the 20 doesn't affect our work in any way. Do you guys all see the triangle we have? We've got a triangle that has a leg of x, a leg of y, and a hypotenuse of 13. So what will be our equation for this? If you're thinking a squared plus b squared equals c squared, you're very close, but we should go with x squared plus y squared equals, well, 13 squared. That's not a variable, so let's just go ahead and put in our number right now, 169. Now, if you remember the next step of a related rate question, we're going to need to take the derivative with respect to time. Now, if you think carefully, this is going to be almost identical to what we've done before. You know we'll get 2x dx dt plus 2y dy dt. But what's the derivative of 169? Well, that's 0. Derivative of a constant is 0. Now, I do want to just bring up one tiny little detail here. Let's say, by mistake, you accidentally did this. You did x squared plus y squared, and let's say you accidentally named the variable for the ladder s squared like before. Okay? Now, in this situation, I don't recommend this because the ladder is not a variable. It's a constant 13. But if you took your derivative and got 2x dx dt plus 2y dy dt equals 2s ds dt. This is actually okay, because I would ask you this question here. What does that variable mean? It's a rate, and it would be the rate at which the ladder's length is changing. So think about it. While the ladder itself is 13, that's what s would be in this case, the rate at which it's changing would be 0 because it's not changing. So in reality, even if you made the mistake of using an s in this case, this entire right side is going to become 0 anyway because ds dt would be 0 in this problem. So you can avoid all that simply by remembering that if you have a constant, just use the actual constant instead of a variable. That way when you take the derivative, it turns into 0 anyway. Okay? So just real quick before we get to naming all of our variables here, again, let's cancel out those 2's. And on the right side, we don't need to cancel anything out. So we will have x dx dt plus y dy dt equals 0. And the beauty of this question is that it's actually easier than the last one. There are only 4 variables to get. So here are the parentheses that show us the layout about what we need to do. And now the layout of what we need to do. And now what I'd like you to do is pause this video and figure out what you think each one of these variables should be. Now don't forget, distances will be our x and our y, rates will be our dx dt and dy dt. And when you're dealing with the rate, make sure you think about if the rate is increasing for a positive number or decreasing for a negative number. Good luck. Okay, welcome back. So I hope you guys were able to go through the actual question and read through it. So let me get to reading the problem over. So we know that our ladder is 13 feet. Leaning against, doesn't matter how big the wall is, but it begins to slide down. During the process, here we go. The bottom of the ladder is sliding away from the bottom of the wall at a rate of 0.5. If you take a look at the bottom of a ladder, how far away it is from the bottom of the building, that distance is called x. So I know that we should write, for that first piece of information, dx dt equals, and here's the warning, is it going to be positive 0.5 or negative 0.5? Well, is this distance x going to be increasing or decreasing? If the ladder is sliding out, x is actually going to be going up. So in this case, I can put positive 0.5. Now then it tells you that we need to actually determine the rate at which the top of the ladder is sliding down the vertical wall. So in this question, what are we solving for? Well, the rate means that we need a rate variable, and the top of the ladder sliding down the wall, that variable is y. So we need to solve for dy dt. Now they do give one last piece of information. It says when the tip of the ladder here is exactly 5 feet off the ground. So notice they're telling you a distance here, and that would be the value for y. So I hope you guys got that when you paused the video. And so if we're going to fill in this information now, we can go ahead and get these numbers into the spots they need to go. Let's try that out. We'll get a 0.5 for dx dt. dx dt, that must go right here. And they tell you that the y value at the moment we care about is 5, so y would go right here. 5. Now they tell us that we're going to solve for dy dt. So since we're searching for dy dt, we don't need to plug in anything there. We just simply want to write the variable down. And there is that problem once again. You've done everything possible for this question, but yet there is still a piece of information missing. So what do? Well, we need to examine this triangle at the instant that the problem talked about. So since we know that we have a ladder that's falling, here's how I see the information they gave us. Here's the ground, here's that building. At the moment they tell us, this ladder has fallen quite a bit, and they tell you that the tip of the ladder is 5 feet off the ground. Now you know the ladder is 13 feet. So I'm not going to give you time to pause this one, because if I said solve for x to use Pythagorean Theorem to do it, I think that would actually be a waste of time. Many of you should know by this point that Pythagorean Triple 5, 12, 13 saves you a heck of a lot of time. So what is that distance right there? What variable would that be? That would be our x. So go ahead and plug in a 12 there. If you notice, we now have everything we need to solve for the one missing variable, so let's do that now. We will get 12 times 0.5, which is just 6, plus 5 dy dt equals 0. Let's solve for dy dt by subtracting 6. So 5 dy dt equals a negative 6. And now we get dy dt is equal to negative 6 over 5. And in this case here, what would our units be for dy dt? This would be feet per second. Now, question for you. Why are we getting a negative answer? How does that make sense in the context of this question? What does dy dt actually represent? Well, going up to our original diagram here, take a look. If y represents the distance from the top of the ladder to the ground, and if that distance is falling, or if the ladder is falling, is y increasing or decreasing? Well, that distance is certainly going downward. It is shrinking. So when we solved for the rate at which the top of the ladder is sliding down, here's what we could say as our final answer to this. Let me get a little bit of room here. I know that our answer was dy dt equals negative 6 over 5 feet per second. But if I want to make a conclusion here, I would say the top of the ladder is falling at a rate of 6 over 5 feet per second. Sorry, that's a 5. And if you're saying, why aren't you saying negative like your answer up here did? Well, the whole point is, if you say the word falling, you're already telling the person that it's shrinking. So if you say falling at a rate of 6 over 5, that would be accurate. You could also say the top of the ladder is, or the distance between the top of the ladder and the ground is changing at a rate of negative 6 over 5. But I think this way of explaining the sentence makes a lot more sense. So, hope you enjoyed these videos. Now try the homework problems from Pythagorean Theorem. Good luck, everybody.